In his book, Faust in Copenhagen, Gino Segre relates a statement made by mathematician Mark Koch. Koch said he divided geniuses into two classes. There were the ordinary ones whose achievements might be emulated by intelligent people through enormous hard work and a good dose of luck. Then came the mathematicians, whose inventions are so astounding, so counter to all the intuitions of their colleagues, that it is hard to see how any human being could have imagined them. While this statement was made in reference to American physicist Richard Feynman, whom we will have occasion to meet later in this episode, it applied even more to the subject of this podcast. Without question, Paul Dirac was a magician. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 17.2, Supplemental. Paul Dirac, the Magician. In 1926, Dirac had succeeded in shocking the world of theoretical physics with his paper generalizing the work of Heisenberg. Heisenberg's matrix mechanics paper, while clearly a breakthrough, had been a discussion of something that might be thought of as a toy problem. He had developed a method to analyze the system of an electron at the end of a spring as a model for what might happen in the hydrogen atom. In this paper, he developed the commutation relationship we've discussed in several episodes, as well as a new mathematical method that relied only on observable quantities. What Dirac's paper did was show that the approach could be applied to any quantum mechanical system, as well as place the mathematical framework on the firm footing of Poisson brackets. This paper served as the basis of Dirac's PhD dissertation, and it established him in the parlance of the faculty at Cambridge as a quote-unquote first-rate man, meaning that he was a rare talent in the academic world. Upon the completion of his dissertation, Dirac accepted a postdoctoral fellowship to work with Bohr's group in Copenhagen. In many ways, he and Bohr were nearly opposites in working style, but the two men got along well, both admiring the other's prodigious talent and insight. Bohr, of course, worked in groups, bouncing ideas off his students, endlessly discussing and debating ideas in order to tease out the best ones. Dirac, on the other hand, closeted himself in the Institute's library for much of the day, working on the ideas he was developing regarding quantum theory. His only breaks were to attend seminars given by the various other visitors and faculty at the Institute, and his daily walks, where he allowed thoughts to come to him as he tried to clear his mind of the work he was doing in order to start fresh. It was at Copenhagen that Dirac showed the equivalence of the Heisenberg and Schrödinger approaches to quantum mechanics, and he began to take the first steps towards establishing what we now call quantum field theory. His work on field theory continued through the next year when he moved for the second year of his postdoc to work with Born's group in Göttingen. He loved the academic German town, which afforded him the opportunity to replicate his work and living environments in Cambridge more closely than he had in Copenhagen. One thing he did take with him, however, from Bohr's Institute was the recognition that it was good to work in the proximity of others and to hear and process their ideas. In addition to his continuing work in field theory, something which he competed with Pascual Jordan rather than collaborate, he formed a friendship with the American Robert Oppenheimer. While Oppenheimer was insufferably arrogant towards many of the physicists at Born's Institute, he seems to have truly respected Dirac's intellect and thus treated him with deference. Their long friendship began here, and it was during this time that a classic Dirac story originates. He and Oppenheimer shared lodging in a boarding house not too far from Born's Institute. While Oppenheimer was wont to indulge in the pleasures of the nightlife in the quote-unquote college town of Göttingen. Dirac tended to stay in. But in any case, they had many opportunities to interact with each other during the time. On some given particular day, Dirac saw Oppenheimer reading some Dante. Ever the literal and logical, Dirac asked Oppenheimer, quote, "How can you do both physics and poetry? In physics, we try to explain in simple terms something that nobody knew before. In poetry, it is the exact opposite." Following his work in Göttingen, Dirac returned to Cambridge, still working as a postdoctoral fellow. Before he returned to his home country, he attended the 1927 Solvay Conference as an invited speaker and presented his field theory work on light. While the work was well received, the conference was really about the Copenhagen interpretation and the ongoing debate between Bohr and Einstein about the issues it contained, something Dirac was not much interested in either at that time or at any other point in his career. For him, trying to determine the precise meanings of quantum theory was an exercise in futility, as the mathematics have been shown not to correspond with any classical pictures in reality. While not quite of the later shut up and calculate school of interpretive agnosticism about quantum mechanics, Dirac felt that the math spoke for itself through its elegance, and that was enough. Upon his return to England, Dirac realized that while he had done excellent work, a great contribution was still needed if he were to be thought of alongside those two preeminent physicists of his time, Bohr and Einstein. When Bohr asked him at the end of the Solvay conference what he was working on, Dirac informed that he was trying to include relativistic considerations into the quantum mechanics of Heisenberg and Schrödinger. Bohr informed him that the mathematician Klein had already solved that problem, but Dirac was profoundly skeptical of the work in Klein's approach, partially because Klein's work predicted that the chance of finding an electron at a certain point in space around an atom was going to be less than zero, an obvious physical improbability. Therefore, it was at St. John's College at Cambridge that Dirac settled into his austere quarters and began working on what would be his opus. Over the course of the next 6 weeks, he tried a number of different things, a number of different approaches of combining the two theories until he hit on the right method in late November of 1927. As discussed previously, his solution was the very essence of elegance, and when it was published, it stunned physicists around the world. Bohr called it, quote, "an absolute wonder," while the American theoretician John Van Vleck called it, quote, "a magician's extraction of rabbits from a silk hat," unquote. John Slater, who had worked with Bohr and Kramers in Copenhagen, was even more effusive. He wrote, "We can hardly conceive of anyone else having the thought of the equation. It shows the peculiar power of the sort of intuitive genius which he has possessed more than perhaps any of the other scientists of the period." More than anything else he did, the relativistic Schrödinger equation, or the Dirac equation as it is now known, was to be his most enduring legacy. Of course, the equation had the problem that it predicted 4 solutions that corresponded to different states of the electron. It would be 5 long years before Carl David Anderson would show that the other 2 states were antimatter electrons, something Dirac began to suggest they would be just a year or so before they were discovered in the observations of cosmic ray decays. Anderson's work would be confirmed and expanded by one of Dirac's colleagues at Cambridge working at the Cavendish, one Patrick Blackett. It is also around this time that Dirac began to make friends at Cambridge amongst the other young researchers, most notably Rutherford's postdoctoral student Kapitsa and George Gamow. While Kapitsa was an experimentalist at the Cavendish and thus separated to a degree from the theorists at St. John's, he and Dirac shared a background in engineering as well as in Marxism, something I'd like to discuss down the road a bit. The two had initially met when Dirac began attending an informal seminar series Kapitsa had organized for the physics research community at Cambridge, and in time, their common interests turned into a bridge by which a relationship could be built. During this time, Dirac would travel often to other institutions to lecture on quantum mechanics. In 1928, he traveled to Europe and the Soviet Union. While on these tours, he began to develop the ability to work with others for the first time, beginning collaborations that would prove fruitful. Most notably, he expanded on the work of John von Neumann in investigating the statistical mechanics of quantum particles. 1929 brought a paper applying quantum mechanics to larger atoms that would prove to be a foundational paper for explaining magnetism in solids. He also traveled to the United States to give a series of lectures at first Princeton, then Chicago, and then the University of Wisconsin. It was during one of his lectures at Wisconsin that one of these just classic Dirac stories is said to have occurred. Dirac had just completed a lecture on some part of quantum theory when the moderator of the lecture asked the audience if there were any questions. One of the participants said something to the effect that he didn't understand a particular equation that Dirac had written on the board. For several minutes, the room was silent as everyone waited for Dirac to respond to the questioner. But he merely went about his business of organizing his papers. When the moderator finally asked him if he wished to respond to the gentleman, Dirac merely replied, quote, "That was not a question, it was a comment," unquote. His trip continued out west, where he alternating lecturing and sightseeing, fitting in visits to the Grand Canyon, which he hiked to the bottom of and then back out of, and Yosemite. In August, he met Heisenberg, who was also on the lecture tour, and the two hiked through Yellowstone on an itinerary Dirac had planned that would allow them to see the maximum number of geysers that would erupt. That's just such a classic thing for Dirac. The two then took a steamer across the Pacific to Japan to jointly lecture there. And herein lies yet another classic Dirac tale. Heisenberg was, of course, a good bit more outgoing than Dirac, and the two of them as bachelors attended a number of social events during the cruise. In these cases, the more rakish Heisenberg took to dancing with a number of the women on the cruise. One evening, as Heisenberg was cutting the rug, so to speak, Dirac was sitting at a table they shared when the German returned to the place where they were sitting between dances for a bit of refreshment. The Englishman asked, "Why do you dance?" To which Heisenberg replied, "When there are nice girls, it is a pleasure to dance." Dirac looked thoughtful. After about 5 minutes of silence, he said, "Heisenberg, how do you know beforehand that the girls are nice?" Upon his return to Cambridge after this around-the-world trip, Dirac continued to work on dealing with the negative energy states predicted by his equation by developing the whole theory discussed in the matter-antimatter episode. While the idea was compelling, it received a lot of resistance and criticism, especially from Pauli, who found it ludicrous. From their time together in Copenhagen in 1924-25, Pauli and Dirac had not gotten along very well, and the two men not so secretly delighted in each other's failures and setbacks. Pauli thought Dirac's holes and later anti-electrons were theoretical hogwash, while Dirac, for his part, ridiculed Pauli's theorized neutrino. It turns out both men were wrong, as both the positron and neutrino would be experimentally confirmed to exist. In February of 1930, Dirac was elected as a Fellow of the Royal Society, the youngest person to have been so honored in many, many years. He celebrated by buying his first car, something he drove rather poorly and recklessly until various statutes were placed on the books in England limiting speed and such. That year, he would also author what is known as the definitive text on the subject of quantum mechanics, the Principles of Quantum Mechanics. While not as accessible in some ways as the texts of Heisenberg and Pauli, it is a masterpiece of mathematical clarity and elegance with little wasted interpretation or flourish. Nature's review of the text gushed. Dirac bids us throw aside preconceived ideas regarding the nature of phenomena and admit the existence of a substratum of which it is impossible to form a picture. We may describe this as the application of pure thought to physics, and it is this which makes Dirac's method more profound than that of the other writers. Even Pauli spoke admiring of the text, calling it a, quote, an indispensable standard work. unquote. It is telling that the three men who would move quantum field theory forward in the late 1940s and early 1950s would all say that they learned the subject by studying Dirac's terse and elegant text. In early 1931, Dirac put forward another piece of groundbreaking work, this time on the nature of magnetism. Since the time of Faraday, it had been known that moving electrical charges could produce magnetic fields. As the study of what would become electromagnetism progressed, it was soon discovered that individual magnetic poles, individual norths and south, something that would come to be known as monopoles, could not seem to be isolated. Whenever magnetic phenomena were observed, there were always two poles, together the familiar north and south. In the first months of that year, Dirac was able to show that quantum mechanics was compatible with the idea of single poles, i.e. monopoles, and that if even one monopole could be shown to exist, it would explain why electric charge is always found in discrete amounts or multiples of a single elementary charge. While this theory, actually more of a hypothesis really, did not guarantee the existence of monopoles, it did show that such things were allowed by quantum reasonings and explained why they might exist. The search for monopoles has long been a holy grail of particle physics, with many efforts being made to detect them. While there have been a few possible detections, each of them has been explainable through other means, and thus it is generally not thought that such a discovery has in fact been made. Dirac suggested that one of the reasons that this might be the case is that monopoles of different sign might be so strongly bound to each other that they might be inseparable at the energies available at the time of his work, something hinted at in the theory he produced. As I mentioned in the last episode, particle physicists at the Large Hadron Collider in CERN are, as this episode is being produced, searching for monopoles at the highest energies ever produced in a particle accelerator or collider. The work may be 84 years old, but it's still powerfully relevant even today. It's a testament to the power and subtlety of Dirac's thinking. Shortly after this, Dirac revised his whole theory to suggest that the particles predicted by his equation from 4 years earlier were not negative energy electrons, but rather anti-electrons, coining the term for the first time in a 1931 paper. Less than 18 months later, as I've noted before, Anderson would produce the first piece of experimental evidence that supported Dirac's antimatter idea. Within a few months of that, Dirac's colleague at Cambridge, Blackett, would produce a mountain of additional evidence, not only of the existence of the particle, but of its production as part of a pair with the electron. Moreover, he would also show the electron and anti-electron's ability to annihilate each other to produce high-energy gamma-ray photons, all as predicted by the Dirac equation. 1932 is sometimes called the miracle year in physics. Not only did Chadwick discover the neutron and Anderson the positron, but the nucleus was first split by Rutherford's boys at the Cavendish. When Dirac gathered around with his colleagues at Bohr's annual workshop on the problems in theoretical physics, the atmosphere was both exhilarating and ominous. Never before had the horizons of physics been so broad and open, even while the world around the bubble of Bohr's Institute of Copenhagen was slowly falling apart and turning towards totalitarianism as a solution to its economic and political problems. Trapped in the morass of the Great Depression, the nations of Europe spiraled towards the abyss that was fascism and political purging. Even as the triumphs of physics were announced, first Crofts and Watson splitting the atom, then Anderson discovering the positron, and finally Chadwick's uncovering of the neutron, Hitler and Mussolini were gaining power in Germany and Italy respectively, while Stalin was instituting the 5-year program and collectivization that would kill some 14 million Russians, more than all the deaths attributed to the Great War less than a generation before. It was also in this year that Dirac was appointed to be the Lucasian Chair of Mathematics, the position once held by Isaac Newton and now held by Stephen Hawking. It It was the recognition that he was the preeminent theorist of all Britain, and indeed, perhaps all physics. Ironically, it also marked the end of the 8-year period of his greatest productivity. Never again would he produce work as obviously insightful and elegant as he had in his youth. This is not to say that he didn't contribute in a number of different ways over the next several years to several sub-disciplines of physics and physical chemistry. Rather, it is probably better to suggest that for a time he got stuck. As I'll discuss in the forthcoming episode on quantum field theory, after the initial successes with the approach, he, Pauli, and Heisenberg got bogged down in trying to solve several serious problems where the mathematics predicted certain physical quantities to be infinite when they clearly were not. Each of the three men expressed despair over the lack of progress being made after 1932 in dealing with these issues. For Heisenberg and Pauli, they were able to turn to other problems of application and thus continue to produce solid work up until and throughout the outbreak of hostilities in World War II. Such applications generally just didn't interest Dirac. For him, it was the beauty and elegance of the mathematics that he sought, and so, once the fundamental theory had been established, he left the work of applying those ideas to others. In several instances, Dirac would put forward a mathematical description of a system that would lead to other talented physicists making significant breakthroughs in those areas of research. At this point, it is probably appropriate to say a few words about some of the parts of Dirac's life outside of physics and mathematics. Early in his time at Cambridge, Dirac fell in with a small but influential group of academics at Cambridge who were either communists or sympathetic to that political ideology. To use a metaphor most recently employed by Dan Carlin, the Germans, under the direction of Erich Ludendorff, had sent Vladimir Lenin to Russia in 1917 to undermine the weak Russian autocracy. In releasing, as Carlin puts it, the intellectual contagion of Lenin's brand of Marxism into that country, the Germans succeeded in removing the Russians as a combatant, but also became infected with the ideas that workers should hold the power in the political state. As discussed in the first of the Heisenberg trilogy, this viral spread of communist ideas into Germany nearly succeeded in toppling the shaky Weimar Republic. In time, the ideas of Marx and Lenin made their way through most of the countries in Europe, especially after a number of them, most notably Great Britain, suffered from deep recessions after the war. In 1925, workers had called a general strike that initially brought the country to a standstill. Unlike in Germany, where the workers managed to gain control of the government in several cities in the 1919 uprising, the upper and middle classes in Britain broke the strike and the movement receded. At Cambridge, a number of the faculty and students joined in the strike breaking, a disappointment for those who hoped that the educational establishment would side with the proletariat. After the immediate crisis has passed, the few faculty who were communists made it their mission to recruit others from the faculty by fostering an exchange of ideas as part of the intellectual discussion. Despite Rutherford's ban on discussing politics at the Cavendish, several of the young scientists, including Kapitsa, there were willing to talk up the ideas of Marx outside of the lab itself. It is through these contacts and discussions that Dirac was first introduced to the idea that Marxism was the only scientifically based political system. Soon becoming sympathetic to the arguments of his fellow faculty, especially after the strike when Churchill championed ordering the troops to violently end the strike while comparing the workers to the quote-unquote German enemies of just a few years earlier, Dirac withheld from officially joining the party or declaring himself in favor of its goals. Nevertheless, he took several trips to the Soviet Union before Stalin clamped down on contact with the West in the mid-1930s. In the realm of religion, it's pretty clear that Dirac was an atheist throughout his early career. While he did not usually speak about his views on religion, there are a couple of instances where his antipathy towards all organized religion did bubble to the surface. The most famous of these was at the 1927 Solvay Conference. According to Heisenberg, the young guns were gathered in one of the smoky lounges of the hotel where they were all staying when the topic of conversation turned to Einstein's habit of bringing up God and his preferences during the discussions regarding the Copenhagen interpretation. Apparently, Dirac had sort of had his fill, both of Einstein and probably some fine spirit, and decided to hold forth a bit, saying that religion was, quote, a jumble of false assertions with no basis in reality. The very idea of God is a product of the human imagination, unquote. He continued by asserting, and again I'll quote here, quote, the postulate of an almighty God is unhelpful and unnecessary, taught only because some of us want to keep the lower classes quiet, unquote. When Heisenberg tried to protest this, Dirac cut him off rather uncharacteristically by explaining that he disagreed with, and again, quote, religious myths on principle, and believed that the best way to decide what was right was to deduce it by reason alone from the situation in which I find myself. I live in a society with others, to whom, on principle, I must grant the same rights I claim for myself. I must simply try to strike a fair balance, unquote. Now, before you react to Dirac's ideas, recall that this is a man whose responses to conversations outside of physics was measured in units of 1 word per hour. In response to this outburst, Pauli, ever the sardonic commentator, was said to have observed, quote, well, our friend Dirac too has a religion, and its guiding principle is, there is no God, and Dirac is his prophet, unquote. To his credit, Dirac is said to have laughed right along with everyone else. More seriously, a few years later, he was spurred to put down what he thought on a number of issues of philosophical and religious content after a bit of a row with British matron Isabel Whitehead. In these notes, he puts forward a set of ideas about what might stand in for the traditional faith in religion. He writes, quote, Orthodox religion would be very suitable for a primitive community whose members are not sufficiently developed to be taught true unselfishness, quote, unquote. Yet, even as Dirac rejects the whole traditional view of faith and its role in society, he posits that a different sort of faith, something not religiously based, is needed for a person to thrive, something to make human life, effort, and perseverance worthwhile. This led him, I should say, to the following credo. He wrote, in my case, this article of faith is that the human race will continue to live forever and will develop and progress without limit. This is an assumption that I must make for my peace of mind. Living is worthwhile if one can contribute in some small way to this endless chain of progress. Now, as Dirac grew older, his atheism seems to have transformed into something more agnostic, with the idea that the underlying beauty and elegance of mathematics might point to something more fundamental in the state of nature or reality. In 1933, the Nobel Prize Committee finally resolved what had been a 3-year debate as how to honor the creators of quantum mechanics. While the 1931 prize in physics was withheld, the 1932 prize was awarded to Heisenberg, while Schrödinger and Dirac shared the 1933 prize jointly. The 3 men attended the ceremonies together, with Dirac and Heisenberg being accompanied by their mothers as they were still bachelors, a state none of Dirac's friends or colleagues at Cambridge could ever see changing. When Dirac returned to the venerable institution's familiar environs, he was still stymied by the difficulties with quantum field theory. As was the case with Heisenberg and Pauli, he did turn to a few other projects to keep busy. The most interesting of these was work he did at the Cavendish with Kapitsa. In the lab, there were a number of researchers who needed extraordinarily pure samples of elements for their research. This included the desire to have samples made of one specific isotope of an element. As each isotope differs only in the number of neutrons contained in the nucleus, and thus they are chemically identical, separation of one isotope of an element from another can really be challenging. In response to this, Dirac turned to his engineering background to see if he could produce a solution to the problem. His approach was to force gas at a high pressure through a nozzle into a tube where it would travel in a spiral path. The idea was that the heavier isotopes would collect at the outside of the stream, while the lighter ones would migrate towards the inside of the spiral. Instead, what Dirac found was that while the isotope separation was fairly inefficient in the stream actually did separate into two mixed paths, with the outer one having a temperature that was about 100 degrees hotter than the inner one. While the experiment was soon set aside as being of limited usefulness, it would be reconsidered just a few years later when the problem of isotope separation became an important thing in the development of fission technologies. In 1934, Dirac took a sabbatical from Cambridge to work at Princeton's Institute of Advanced Study with Einstein. While there, he reworked his combination of relativity and quantum mechanics using something known as de Sitter geometries. While the approach once again provided an elegant mathematical framework, it didn't resolve the problem of infinities in quantum field theory. While there, he also produced a second edition of his textbook that was even more accessible than the first had been. The most profound outcome, however, of the year's work is that he met the woman he would marry. Over the previous year, Dirac had developed relationships with a couple of women, including George Gamow's young and beautiful wife, Rose, that seemed to have drawn him out of his shell somewhat. While it is unknown if these friendships ever developed into something more intimate, they certainly introduced Dirac to the charms of the fairer gender. While in Princeton, Dirac was introduced to the sister of the youngest member of the Institute, the Hungarian physicist Eugene Wigner. One day, Dirac joined Wigner and Mansi, his sister, as she was known, for lunch, and over the course of the year, the two developed something of a friendship. When Dirac returned to Cambridge, he stayed in touch with Mansi, traveling to meet her either in her home country or other European locales. The two would be married in 1937, with Dirac taking in Mansi's two children from a previous marriage. Within a few years, they would add two daughters of their own. While the relationship was an occasionally stormy one, Dirac and Mansi would remain together until his death in 1984. With the onset of the war, the Diracs would endure the Blitz at their home in Cambridge. Paul declined several offers to work on decoding projects and specific atomic bomb-related projects at several times during the conflict, though he did do additional work on isotope separation techniques. He also continued his work to resolve the infinities that kept cropping up in quantum field theory, introducing the idea of an indefinite metric in 1940, even as the bombs were falling around his home. It was another elegant piece of mathematical work that impressed even Pauli and was a precursor to some of the renormalization theory work done following the war. During the middle years of the conflict, Dirac did some theoretical work on fission theory, but in 1943 he seems to become convinced that the Allies would win in Europe without the bomb, and, as a result, he withdrew from further efforts shortly after the British and American projects were joined. Near the end of the war, he worked on a third edition of his text, wherein he introduced what is known as bra-ket notation, something every student of quantum mechanics learns and uses today. At the war's conclusions, Dirac tried to get back to his normal routine as quickly as possible. In 1946, he attended a conference in Princeton, given to mark that institution's 200th anniversary. It was at this conference that he met a 28-year-old Richard Feynman, who had been working on extending something Dirac had written in a short paper he had published a few years earlier on what is known as least action principle. While not usually counted as being among Dirac's greatest works, it laid out an alternative way of doing quantum mechanics that was different but equivalent to the methods of Heisenberg and Schrödinger. Feynman had studied the paper carefully and found that there were additional insights to be mined. He approached Dirac to ask about the work he was doing and received little more than a, quote, "That's very interesting," kind of response. Nevertheless, that small acknowledgement and encouragement meant that Feynman was onto something worthwhile. He went on to develop Dirac's least action approach more fully, something that established him as a first-rate physicist and brought him a good bit of notoriety. For his part, Feynman was always quick to point out that he had done very little new work, but that he was only representing Dirac's original ideas. In 1947, the first experimental results came out that showed that the Dirac equation was unable to give correct predictions for specific types of systems and experiments. While this may seem like a setback, the new results actually showed a way forward for physics which seemed to be stuck in terms of possibly resolving some of the issues of field theory for the first time in 20 years. Within 2 years, Feynman, along with Julian Schwinger, were able to explain the results of the experiments using methods developed from this least action principle. Feynman, in particular, developed a graphical representation of these processes that came to be very helpful in understanding this approach, his so-called Feynman Diagrams. These results turned out to be very similar to the work of a Japanese physicist by the name of Shinichiro Tominaga, who had worked from Dirac's version of quantum field theory. It fell to the brilliant mathematician and physicist Feynman Dyson to show, much as Dirac had done in 1925 with the quantum mechanics of Heisenberg and Schrödinger, that the three approaches were, in fact, equivalent. For their work, Feynman, Schwinger, and Tominaga would receive the Nobel Prize in Physics in 1965. So brilliant were Feynman's contributions that Dirac's friend and brother-in-law, Eugene Wigner, once said, quote, "Feynman is a second Dirac, only this time human," unquote. Unfortunately, the work of these three men was not much appreciated by the fountainhead of their insight. Dirac found the mathematics of their work ugly and inelegant, and thus felt that while the theory could explain the interaction of an electron with a photon, the tricks it used to deal with the infinities that had so bedeviled his approach rendered it irrelevant. No matter how well Feynman's quantum electrodynamics, or QED as it was called, accounted for the experimental data, something it does, by the way, astoundingly well, Dirac would never accept it as the final answer. He never let go of the idea that there was a more mathematically beautiful solution to be found that would consign QED to the trash heap of physics. While there are indications that modern twist-or theory may point to such a resolution, it is still unknown as to whether this approach will finally do away with the tricks of renormalization, as it was called. In 1955, after another around-the-world trip, though this one was fraught with illness, injury, and tragic loss due to the death of Einstein, Dirac announced his one final great contribution to physics. The place for this initial announcement was rather odd, as it was the quantum mechanics class he taught at Cambridge. I can't imagine what it must have been like to be a first-year graduate student in a class being taught by someone as prestigious as Dirac. But for him to have come into the classroom and said, "I've just done this work. It could be important. I want you to learn it," must have both just electrified and terrified his students. The work was a reconceptualization of what particles actually were. First put forward in a series of lectures given in Ottawa the previous summer, the full theory said that the universe is not made up of point-like particles, things like traditional electrons, photons, and by this point, numerous other members of the subatomic zoo, but rather by tiny, one-dimensional objects Dirac called strings. In other words, Dirac was the first physicist to put forward one of the most engaging ideas in present-day theoretical physics, that of string theory. While the ideas presented were incomplete, they did find a way to represent the interactions between electrons and photons without either the infinities present in QED nor the renormalization Feynman had used to deal with them. While not fully appreciated at the time, string theory would be taken up a generation later and developed into a much fuller and more robust set of ideas. At this point, I will bring this scientific biography to a close. In 1969, Dirac would retire from Cambridge and immigrate to Tallahassee, Florida, to take a distinguished position at Florida State University. He would continue to participate in various discussions on both quantum mechanics and relativity, and would do much to shepherd that reemergence of string theory, most notably with Pierre Ramon at the University of Florida. Dirac was also enraptured by spaceflight and was beside himself when Neil Armstrong became the first human to set foot on the moon. Still, however, Dirac felt that his life had been something of a waste. In a conversation with Ramon, Dirac shared that he still felt he couldn't explain the simple interaction of an electron with a photon, and thus his life's work had been a failure. Of course, the verdict of history is that Dirac's life was not a waste. His contributions to the progress of quantum mechanics are, without question, peerless. Following his death in 1984 in Tallahassee, Dirac was buried there. 11 years after, he was given a marker in the Science Corner of Westminster Abbey alongside Newton and Rutherford, inscribed with a version of his equation, perhaps his most profound achievement. His most lasting, I would argue, was his text on the subject, however. Generations of physicists and chemists have used the sparse language and mathematical notation found therein to understand the fundamentally strange nature of reality at the atomic level. Its presentation has inspired several Nobel Prize winners, including the aforementioned Feynman, Schwinger, and Tominaga. Even as the Dirac equation has been superseded by more powerful, if not more elegant, descriptions of the physical universe, the teaching tool Dirac created in the text continues to shape the minds of successive generations of researchers. This legacy alone gives lie to Dirac's most deeply held fear. In our next episode, we'll return to the narrative and look at the idea that Dirac, along with Heisenberg, Pauli, and Jordan, first put forward that was the source of some of their darkest moments, quantum field theory, in an episode entitled Of Fields and Particles. Until next time, full sails on your journey.